Better get started. Look at our schedule for a minute. So we're supposed to be on chemistry chapter 2. And so you're going to be so glad you came today because you're going to learn all about chemistry. Um, Chemistry is not my favorite thing. Um, you major in biology at a university, you have to take at least 2 whole years of chemistry. And I never really liked it, never felt that I was very good at it. And I was able to learn this stuff, but I didn't really feel like I really get it. It's like I don't really understand it. But I think for that reason, I do okay teaching it because I've never forgotten how hard it was for me to learn it, so I try to make it as simple as I can for students. That's right. We didn't start this chapter yet, right? Okay. I get confused with other classes. I've taught this basic chemistry in three of my classes already this semester, so I get confused. This guy Thomas Huxley was a biologist at the time of Charles Darwin in the 1800s, and he's nicknamed Darwin's bulldog because when Darwin published his ideas about evolution by natural selection, it was met with a lot of resistance. Just like now, a lot of people don't accept it, and but this Huxley believed it, and he was very vocal and very assertively defended Darwin. I think this quote of his refers to the disappointment that happens when you come up with a hypothesis that seems to be perfect. You seem to perfectly explain how or why something happens, but then after testing it, it turns out it's not right. It's not true. This term "beautiful" is often used by scientists to describe such a hypothesis that seems to perfectly answer the question or explain something. Okay, chemistry is about matter and how matter changes. Matter, the definition of matter says here, physical substance that occupies space and has mass. So it's just physical stuff. An example of something that is not matter would be energy, because energy does not have mass. It doesn't take up space. And all matter is made up of atoms. Much of this chapter is about atoms, the structure of atoms, how atoms interact with each other in chemical reactions. But there are many different types of matter that we call elements. About 118, I think, elements. And how the different elements are different from each other is they have different atoms. And the difference in the atom is the size of the atoms. How many protons, neutrons, and electrons are in the atoms of, for example, hydrogen is different from the number of protons, neutrons, and electrons in oxygen or carbon, other elements. And we'll talk about what those particles are, protons, neutrons, and electrons, in a minute. Each element has a symbol, which is what's in parentheses here, and these examples of elements. In many cases, it's just the first letter. of the word. Um, what's that? Right. Yeah. So that's doesn't make, why is it Fe? There's no Fe in the word iron. Um, that's because the symbol is from the Latin word for iron, which is ferra. Um, and in fact, metals that have iron in them, like steel, is sometimes called a ferric metal because it has iron in it. And there are other examples, like you mentioned gold is what uh, Au, silver is Ag, um, mercury is Hg, sodium is Na. Those symbols that don't seem to make sense. They're usually because they come from the Latin word for that element. Um, Some of them have two letters. Some of them, there's a few that have three letters, a capital letter and two lowercase. Um, and what else? So here's a one type of diagram of an element of an atom, and so it shows the three what we call subatomic particles: the protons, neutrons, and electrons. And the this cluster of particles in the center here is called the nucleus. That's where the protons and neutrons are. This word nucleus, we use that word in cells also. So a cell has a nucleus. That's where the chromosomes are. So don't be confused by that the nucleus of an atom and the nucleus of a cell. It's the same word, but completely different meanings. But, out here, shown on this circle, are the electrons. And the plus and minus signs refer to the static electric charge on those particles. So the protons have a positive static electric charge. The electrons have a negative static electric charge. The word static means not moving. So this is not like electricity flowing through a wire. This is just an electric charge that's stuck on that electron and on that proton. The neutrons have no electric charge, so we say they're electrically neutral, or they have their electric charge is zero. And the number of electrons in a normal atom is the same as the number of protons. Not in all atoms. We'll see that atoms can gain or lose electrons in a few minutes. But so if there's the same number of positive protons as positive electrons, then the overall atom we would say is electrically neutral. Same amount of positive stuff as negative stuff. These electric charges are the same size, but one's positive and one's negative. What do we know about opposite charges? How do they affect each other? Opposites attract. Opposites attract. So these electrons are attracted to the neutrons or the protons. So why don't they get sucked in there into the nucleus? It's because they're out here spinning so fast with so much energy. Kind of like the planets revolving around the sun. There's gravity, strong gravity between the sun and each of the planets. But why don't the planets get sucked into the sun? It's because they're out there spinning, and the centrifugal force balances the gravity, so they stay in their orbits at some distance out from the sun. So these electrons are shown on this circle. We call this an orbit, or it's also called an electron shell or an energy level. Any of those terms mean the same thing: orbits, electron shells, energy levels. It's shown as a circle, but the electrons, so they're spinning real fast out here in that orbit, but they don't stay exactly that distance away from the nucleus. They can move closer and farther. And some diagrams of atoms show it as a cloud of electrons, just where, but this is the average distance out from the nucleus where these electrons are spinning. We talked about this. Okay, the atomic numbers. So it equals the number of protons in an atom. So that's what determines what element an atom is, how many protons it has. So this one we just looked at, 2 protons. I just happen to know that that's helium, the element helium. Atoms, every atom of helium has 2 protons. If it has a different number of protons, it's not helium, it's something else. Um, uh, the mass number is the number of protons plus the number of neutrons in an atom. And then look at this guy again. 2 protons and 2 neutrons, so 2 plus 2. The mass number of this is 4. In this case, the number of protons is the same as the number of neutrons, but that's not usually the case. They're usually different numbers. And this word isotope, it refers to atoms of the same element with different numbers of protons. So we keep jumping back to this. So most helium atoms have 2 neutrons, but I agree, 99.9% of them have 2 neutrons, but there are some helium atoms in the universe that have 3 neutrons. And so we call them isotopes. Same element, just different number of neutrons. Okay. So if I would give you, and this will be on an exam, the next exam, first exam, if I tell you the atomic number and the mass number of an atom, you should be able to tell me how many protons, how many neutrons, and how many electrons are in that atom. So let's do one. If I tell you the atomic number is just going to make this up, 27, and the mass number is 52. And I would ask you, what's the number of protons, number of neutrons, and the number of electrons in that atom? So what's the number of protons? That's the definition of atomic number. So it's 27. That should be easy. And I said the number of protons and electrons normally is the same. So what will be the number of electrons? Also 27. It's easy. So how did you get the number of neutrons? So this is the number of protons. This is the number of protons plus neutrons. So just subtract the little number from the big number, right? So what is that, 25? So that should be easy, right? Everything's easy if you know how. Okay, an example here of isotopes, carbon. Most carbon atoms have 6 neutrons, so 6 protons plus 6 neutrons would be 12. So we call that carbon 12. That's the mass number, 12. Carbon 13 has 7 neutrons. Even in carbon 14, it has 8 neutrons. So there's at least 3 isotopes of carbon. Okay, here's the periodic table of the elements, and there's one on the wall in here. Used to have chemistry classes in here. So this is just a big table or chart with all the elements, and they're arranged in a particular order on there. This is called the periodic table. It's called the periodic table because a row is called a period. Each one of these rows is called a period. The columns are called groups, but they're arranged in a particular order. So from the smallest atoms, and then going across, they increase. So this number in the upper left corner is the atomic number. So hydrogen, H, has 1 proton, and up here helium has 2, and then back here lithium has 3, beryllium 4, 5, 6, and so on. So they get bigger going across the more particles across each row and also down each column. Why are they arranged in why are they in these different rows? Like, what's the difference? What's different about the different rows? It's well, we need to talk a little bit more about those electron shells. Oh, well, I'll come back to this in a minute. But electron shells, we saw that in that helium atom that there were only 2 electrons, and they were in that one orbit, right? But here's carbon has six electrons, but only 2 of them are in that first orbit, the one closest to the nucleus. But then the other 4 are out here in a second electron shell. That's because in any atom, this first electron shell can only hold 2 electrons. And so this one has more than 2, so the rest go in the second shell. But we also need to know that let's find a bigger, here's sodium. It, in the second shell can hold 8. Can only hold 8 electrons. The third shell can hold only 8. That's called the octet rule. Oct means 8, something like octopus or octagon. So if we look back at the periodic table, the atoms or elements in the first row have only 1 electron shell, because that shell can hold only 2. This one has 1, this one has 2, so lithium has 3, so the third electron has to go in the second electron shell. So all of these in the second row have 2 electron shells, all these have 3 electron shells, and 4, and so on. And in the column, in this first column, all of these in this column have the same number of electrons in the outer electron shell. So we just looked at this one, sodium, Na. It has its atomic number is 11, so it has 11 electrons. And they're arranged 2 in the first shell, 8 in the second, and only 1 in that third shell. So like you saw that all of them in that row, or all of the elements in that row, the first row, have 1 electron in their outermost shell. But in this one, it's that 1 electron is in the first shell. This one's that 1 electron is in the second shell. And the sodium we just saw, it's 1 electron in its third shell, which is the outer shell. So that's why they're arranged this way. This bunch of elements has got an arrow, like they're down here separately from all the others. And to be honest, I don't even remember why they do this, but I don't care. You don't have to worry about it. But, in fact, as biologists, we don't have to worry about any of the elements down here. because the the elements that occur in living organisms like us, there's only about 25 of these 118 that naturally occur in or make up our bodies. And these are out, they're all up here. They're all smaller ones, like hydrogen, um, carbon, nitrogen, oxygen, chlorine, sulfur, phosphorus, magnesium, sodium, potassium, copper, zinc, so on. But think of the iodine down here. This is the biggest one. We have iodine in our thyroid glands to make hormones, um, but the rest of these all down here, they're not in living organisms, so I don't care about them. Some of them, unfortunately, we do have, like there's mercury and lead. Lead is down here somewhere. Arsenic, those are all heavy metals. They're toxic. They don't belong in us, but all of us probably have some mercury and lead in our bodies. You eat a lot of tuna, you probably have mercury. Used to be lead in gasoline up until what's it, late 1970s or so. Um, um, so the exhaust that came out of the tailpipe of every car had lead in it. So there was a lot of lead in the environment, and everybody had lead, a lot of lead in their bodies from that reason. But the Environmental Protection Agency put an end to that. This is carbon dating. I mentioned this. Talk about this for a minute. We saw that carbon has these three isotopes, carbon 12, 13, 14. This one, carbon 14, is a radioactive isotope. You've probably heard that term, radioactive isotope. That means what is carbon? That means in an atom of a radioactive. Well, let's go back and look at this one because it shows the protons. When you said opposite charges attract, what do like charges or the same charge? How do they affect each other? They repel each other, push each other apart. So how can that be? How can these protons stay together in a cluster in the nucleus if they repel each other? Why aren't they pushing each other? That's what you've heard of nuclear physics. That nuclear physics is what goes on in the nucleus of an atom. And Albert Einstein figured this out. Why and how do they stay together? And I'm not smart enough to understand that stuff, but there's some mysterious force in the nucleus of an atom that holds those protons together in there. So there's a lot of energy in the nucleus of an atom. That's why if you split the nucleus of an atom, a lot of energy is released. That's how an atomic bomb works and nuclear power plants. That's why you can get so much energy out of a small amount of radioactive material in a nuclear power plant. They're very, very efficient way to generate electricity. Kind of dangerous. But in a radioactive isotope, say that the nucleus is unstable, so it's not holding itself together like normally happens in an atom. So once in a while, a proton will fly out. Very high energy will fly out of the nucleus, and that's the what we call radioactivity, or that's very high energy particles. If they hit us, you can get what do we call it, radioactive illness or something. Um, People who work in nuclear power plants, they always have this thing in the pockets. It looks like a pen, but it's measuring how much radioactivity is receiving them. They take it out and look at it. A little display. They'll tell them how many rads, units of radiation, they've been exposed to. And if that number starts to rise real fast, it's time to leave because there's a leak somewhere. But anyway, so that the rate at which a radioactive atom, we say it decays, which means it has particles flying out. That rate is constant. So as far as we know, it's not affected by temperature or pressure or anything. The the that rate of radioactive decay stays the same. And so for carbon-14, it's been measured. We know that it takes 5,730 years for half of any amount of carbon-14 to decay. So if you have a gram of carbon-14 right now, then this many years from now, only half of that will be left. The rest of it will have decayed and turned into another element. It's losing protons, so it turns into lead. It's not carbon-14 anymore. So we can use that concept to figure out how old a fossil is, because when an organism like an animal is alive, it's always exchanging carbon with the environment. You're eating food with carbon in it and inhaling carbon dioxide. And, so the amount of carbon-14 in your body is about the same as in the environment. But when you die, if your body would turn into a fossil, then 5,730 years from now, that fossil would have only half as much carbon-14 that was in your body when you died. So we can use that fact to, if we find fossils, and we can use that to figure out how old the fossil is. So if we know how much carbon-14 is in the environment, or how much there was 20,000 years ago, and we can compare that, like that percentage of the carbon to the amount of carbon in that fossil now. If it's only half, then we know that fossil is this old. If there's only 1/4 as much as would have been in that animal when it was alive, then it would be 2 half-lives old, so 11,000 years old. So this works for relatively recent fossils. So because that's a pretty short period of time, so this wouldn't be very good for dating the fossils of dinosaurs. How long ago did the dinosaurs disappear? What? Million? Billion? No, it's 65 million. You should all remember, 65 million years ago, the dinosaurs went extinct. Someday your kids are going to ask you that, because kids love dinosaurs. It would be cool if you knew the answer to that. 65 million years. So that's a lot of half-lives. A dinosaur fossil probably has so little carbon-14 left in it that it wouldn't even be measurable. So this would work for something 10,000 or 20 or 30,000 years old, but millions of years, there are other radioactive isotopes in the environment that can be used that have way longer half-lives, like in the millions of years. Okay, where were we? Okay, so who cares about how many electrons are in the outer shell of an atom? Why is that important? It's because of the stable and unstable atoms. If an atom, like this one, neon, it its outermost shell has 8 electrons. That's all it can hold. So that, you say that atom, its outermost shell is full. So that tells us that this atom is stable. Stable and unreactive. That means it's happy the way it is. Um, uh, this one, carbon, this outermost shell has only 4, could hold 8, so it's not stable. This is an unstable and reactive atom. That means if you mix this with some other unstable reactive atoms, there could be a chemical reaction. You mix this stuff, there would never be a chemical reaction. So a chemical reaction is just like when 2 atoms come together to form a molecule. A molecule is just 2 or more atoms stuck together. So other chemical reactions break molecules apart. But this will never connect with another atom and make a molecule. So there's no such thing as neon dioxide or anything like that. Neon is always just neon. It's happy by itself. But this guy is not so happy. He wants to be stable. He wants to get his outermost shell full of electrons. So how he can do that is to hook up with other atoms and get its outermost shell full of electrons. And we'll see how that works in a minute. So that's neon. We said is stable. Let's look in the periodic table again. Where is neon on here? It's here. And this column all the way over to the right, all of these are stable because they all have their outermost electron shell full. So these are called the inert gases. Inert means inactive or unreactive or stable. Also called the noble gases sometimes. I don't know why. But these are all so helium, neon, argon, and so on. So these never form molecules. They're always by themselves. They're stable and happy. They don't need to form molecules. In fact, you guys ever heard of the Hindenburg disaster? You know what that was about? It was over 100 years ago. Back in the early days when they first started making these big airships, like the Goodyear blimp, lighter than air. It's like a big balloon with a little passenger compartment under it for people. And nowadays they have helium. It's a very small atom, so that's why helium is lighter than air. The atoms are very small. But back in the early days, they filled them with this, hydrogen. It's also very small atoms, lighter than air, work fine, except, is this stable? This 1 electron it's in the shell that can hold 2. So this is hydrogen is unstable and reactive. That means there can be chemical reactions. So in fact, hydrogen is very flammable. It can burn. In fact, you could run your car on hydrogen. It'd be a perfect fuel because burning is just a chemical reaction of some kind of fuel with oxygen. If hydrogen would burn, what do you get if you mix hydrogen and oxygen? Can you think of a molecule that has only hydrogen and hydrogen and oxygen? Water. So you just have water vapor coming out the tailpipe, no pollution. But we don't do that because it's very, very hard and difficult and expensive to make pure hydrogen and compress it into a tank and put it on a car, but someday maybe. So think it's a good idea to make a big airship, fill it with hydrogen. It's flammable. The Hindenburg was the name of one of these big airships, and one time there was just a spark, and the whole thing burst into flames. 20-some people burned to death, burned up and died on that thing. So That was a very hard lesson. Don't use this stuff. Use helium. Helium is inert, can't burn. Perfectly safe. So, um, uh, okay, so you talk about this for a second. Ions. I said that in a normal atom, the number of electrons is the same as the number of protons, but that can change because an atom can gain or lose one or more electrons. So this is sodium again. It has only one electron in its outer shell. It would like to have its outer shell full, be stable. Um, and one way to do that is to lose that one electron. Then the second shell would be the outermost, and it's full already. Um, but then it would have fewer electrons than protons. And so now it has more positive protons than negative electrons. So now, like you say, the whole atom has a net electric charge. It's positive. Um, so the total charge on that atom is a plus. If it would lose, if an atom would lose 2 electrons, then it would be a 2 plus. For that. But any plus, that tells us that is what we call an ion. It's an atom that has gained or lost electrons, so that now the atom has an electrical charge. If it's a positive electrical charge from losing electrons, like the sodium did, then that's called a cation. If it is negative, because the atom gained electrons, then we call it an anion. So chemical reactions can make molecules. What would it benefit two atoms to come together? What's that? They want to be stable, and they can become stable if they come together and form molecules. How would that work? First of all, a molecule, again, 2 or more atoms stuck together, and what holds them together we call a chemical bond, and that's what we'll talk about in a minute. But this word compound, you got it in parentheses as if it means the same thing as molecule, but it's not exactly the same. It's almost, the words mean almost the same, but because a compound is 2 or more atoms held together, but it has to involve at least 2 different elements. So for example, this H2O. Everybody knows what that is, right? Water. The way it's written here, this 2 means that this molecule has 2 hydrogen atoms in it. And if there's no number here, that just means it's 1. But so a molecule of water has 2 hydrogen atoms and 1 oxygen atom. So that's a molecule. It's 2 or more atoms stuck together. It's also a compound because there are at least 2 elements, hydrogen and oxygen. So that's a molecule, and it's also a compound. But something like this O2, oxygen, that's two oxygen atoms stuck together. That's a molecule, but is that a compound? No, because it's only 1 element. Right? So chemical reaction is written like this. The reactants. For combining like hydrogen and oxygen, those would be called the reactants or the reagents, sometimes called. So we have H plus O, and then an arrow represents the chemical reaction. And then the product would be what we have after the chemical reaction. So you combine H plus O and then H2O. So those 2 atoms came together to form a molecule. And on the left side of the arrow, there would always be the same elements as on the right. So So in a chemical reaction, elements never change from one element to another. They just rearrange, or they combine, or they separate. So there would never, if there was a carbon on this side, there would always be a carbon on the right side. So there'd always be the same elements on the left side as on the right side. So there's two kinds of these chemical bonds that hold atoms together in molecules, and they're called ionic bonds and covalent bonds. And ionic bonds, pretty simple. We said opposite electrical charges attract. So what do you think would happen if a positive ion and a negative ion came close to each other? They'd be attracted and stick together to form a molecule. That's all an ionic bond is. It even has the word ion in the word. That's here's an example of that happening. Again, there's our friend sodium again. It has got one electron in its outer shell. It's unstable. It would like to be stable. Chlorine, it's got 7 in its outer shell. So it's like it would need just one more to be stable. So what happens when a sodium and a chlorine atom come close to each other? The sodium would like to get rid of that electron to become stable. The chlorine would love to receive it, so that's what happens. This electron goes from the sodium onto the chlorine. Now they're both stable, happy, but now they're both ions. This one has lost an electron, so it's a positive ion. This one has gained an electron, so it's a negative ion. They're attracted to each other, so they come together and stick, and now it's a molecule that we call NaCl, sodium chloride. What is that stuff? Sodium chloride. Anybody know? You ever use it? Ever eat it? Put it on your breakfast. It's just salt, table salt, sodium chloride. Held together by ionic bonds, and that tells us here these dissociate in water. So if you put salt in water, the two ions separate from each other as the salt dissolves. Okay, the other kind of bond that holds atoms together in molecules is covalent. Co means together. Valent, the word valent, the valence electrons are just the electrons in the outer shell. And those are the ones that form bonds, or that participate in making bonds. So why would, well, how that happens? For example, here's hydrogen. You said, this is the one that was in that airship that was unstable and it burst into flames. So these are unstable. Got just one electron in that outer shell. So how could they become stable if they come together and like this? And now they're sharing those electrons with each other. So instead of just this electron spinning around this nucleus and this is spinning around the nucleus, now both of these electrons are spinning around both of them, kind of like a figure 8 or something. So they're sharing those two electrons, and that sharing of electrons holds them together. Why would they want to do that? Because now it's as if each one has 2 electrons, right, around in its outer shell. So now they're both stable and happy. Just like people, married people are always happier than single people, right? So, I'm kidding. Sometimes they are. So that is stable. We say it's stable. It's unreactive. Oxygen does the same thing. Oxygen needs. We have a picture of that. But oxygen has 6 in its outer shell, so it needs 2 more to be stable. So if 2 oxygen atoms come together, they'll share 2 pairs of electrons. We call that a double covalent bond. Nitrogen does that. It shares 3 pairs of electrons to become stable. We call that a triple covalent bond. But so if this is stable, I mean, this is how the hydrogen in the air around us, most of it is like this. Um, uh, and same with oxygen. Most of the oxygen in the air that we inhale is O2. In fact, on a tank of oxygen like they use in hospitals, it has on there O2, not O, but O2, because oxygen normally occurs like this. We know that diatomic molecules, just two atoms, diatomic. So if oxygen is stable and hydrogen is stable, how could that be flammable? If that's what was in that airship and it's stable, how could it burn? Am I lying if I say that's stable, unreactive? It's because it's true that if you mix hydrogen and oxygen together, nothing will happen. It won't burst into flames or anything. But what if you put a spark to it or some fire to it? Just that little bit of energy could cause some of these hydrogen atoms to separate from each other. And same thing with some of the oxygen separate from each other. Now they're unstable again, and now they'll come. They will. So an atom of hydrogen like this and an atom of oxygen by itself, just they'll come together and they will burn. They'll have a chemical reaction, and then that burning will produce more heat. That'll cause more of these to come apart and more oxygen to come apart. So it keeps itself going. So let's go to activation energy. You just need to add a little bit, just a spark, or light a match, and it'll cause some of these to come apart, and some of the oxygen to come apart. Now they're reactive. Now they'll burn and produce more heat to cause more of them. So it's like a chain reaction. It'll keep itself going. But as long as they're together like that, they're stable. Okay, so that's called a covalent bond. Covalent, they're together and they're sharing their valence electrons, the outer shell electrons. Oh, you gotta send around the sign-in sheet to get the column under today's date. Okay, so covalent bonds can be either polar or nonpolar. And the word polar means something is different at the opposite ends. Like the Earth has a north and south pole. A magnet. A magnet has what we call a north and south pole. So if you turn magnets toward each other in one orientation, they'll attract each other. If you flip them around, now they push each other apart. So they're polar. Bipolar disorder means that a person, it's a mental illness in which a person has two opposite moods, either too happy or too sad. A polar molecule is one that's different at the opposite ends. So, in different electrical charges, let's say. This is a water molecule, which is polar, but this is oxygen. Two lines represent that double covalent bond, so it shares two pairs of electrons. So this is non-polar. There's no reason for one of these oxygens to be electrically different from the other, like this one positive and this one negative. They're the same thing. So this is a non-polar molecule, but water is a polar molecule. It's this weird symbol here. It's a Greek letter delta, lowercase delta. Uppercase is just a triangle, but in chemistry that means a partial electrical charge, and the negative sign means the minus sign means this would be a partial negative charge, and at the oxygen end of this water molecule. The hydrogen end has a partial positive charge. In a water molecule, oxygen with two hydrogens, the hydrogens are off at an angle on one side. They're not opposite each other. It's actually like this. And So what would make the oxygen end partially negative and the hydrogen end partially positive? Because these electrons this oxygen is sharing electrons with each of these hydrogens. So, so the electrons spinning around the oxygen and around the hydrogen and around this hydrogen as well, sharing those electrons. But again, opposites attract. The electrons are negative, protons in the nucleus are positive. These hydrogens have just one proton in the nucleus, not much positive stuff in there. This oxygen, this atomic number is 8. It has 8 positive protons in the nucleus, way more positive charge than this is one little proton. So these electrons, as they're spinning around this hydrogen and this oxygen, they're going to maybe spin around that oxygen 3, 4, 5 times, and the hydrogen only once, and 3, 4, 5 times, because the electrons are more attracted to those 8 positive protons in the oxygen nucleus than the one in the hydrogen. So because the electrons spend more time at the oxygen end and less time at the hydrogen end, then we'd say the oxygen end of this molecule is partially negative. Just a slight negative charge. It's not like a whole charge, like a whole electron, the amount of charge on an electron, just a slight charge. And this end is slightly positive. So we say it's a polar covalent bond. Unequal sharing of the electrons causes one end of the molecule to be positive and the other end to be negative. So this molecule, we would say is polar, a polar molecule. Who cares? What's that? Who cares if a molecule is polar or nonpolar? It turns out that can be pretty important, because this is these are 3 water molecules in liquid water, and again, there's those the symbols for the positive hydrogen end and the negative oxygen end. So it turns out that in liquid water, the negative oxygen end of this water molecule is attracted to the positive hydrogen end of this water molecule and to this one. And so these dashed lines represent those weak attractions between these separate water molecules. And those are called hydrogen bonds. And I wish we didn't use the word bond for that, because we said that ionic bond and covalent bonds hold atoms together in a molecule. This is not that. This does not hold atoms together in a molecule. So we shouldn't call it a bond. It's just a weak attraction between separate water molecules. Well, why is that important? You all know about this. You've seen this, probably learned this when you were little kids, that if you fill a container, fill a cup with water, and fill it all the way to the top, if you're careful, you can pile up the water a little bit above the rim. And gravity is trying to make it spill over, but it's like there's a skin on top of that water that allows it to pile up a little bit. How is that possible? Why is that? It's because of this, hydrogen bonds. Well, these water molecules in here have these weak attractions pulling them toward each other, including at the top. So it forms it's like a skin on top of the. Anybody know what that's called? Surface tension. And this is why insects can walk on water. Some insects can do that. Some spiders can walk on the surface of water. You can even, if you're careful, you can float a needle on the surface of water. because of that surface tension, because of these hydrogen bonds, because water molecules are polar. Um, uh, so an example of something that is nonpolar is gasoline or oil. Oils are nonpolar. And so if you try this with gasoline, you fill it up to the rim, you put one more drop in, what do you think would happen? It'll spill right over because there's no hydrogen bonds, no surface tension. An insect could not walk on the surface of gasoline. It would just poke through the surface. Um, uh, um, so, other properties of water. Water is unusual in that it's different from other liquids or substances that can be liquid or solid, but because of the hydrogen bonds. For example, we say it has a high heat capacity. It takes a lot of energy to heat water, to raise the temperature of water, compared to non-polar liquids like gasoline or oil. So if you would take 2 pots of, put them both on burners on the stove and turn it on high heat, so you got the same amount of heat going into both of them, put water in one of them and gasoline in the other. It's a bad idea, don't do that. But the gasoline would heat up much faster. The temperature would rise much faster because the water would heat up slower because heat energy is just the motion of the atoms and molecules in a substance. So in liquid water or in air, the atoms and molecules are always bouncing off of each other, moving real fast. The faster they're moving, the hotter it is, the higher the temperature. So you add heat to this, the heat is going to be getting these molecules moving faster, but they have hydrogen bonds pulling them together. That's going to resist that motion. So it takes more energy to get the atoms and molecules moving faster because of those hydrogen bonds. Gasoline, no hydrogen bonds. It just freely, the molecules just move very freely. And heat and energy, they'll move faster, they'll heat up. And another thing, comparing polar and nonpolar, if you mix something polar like water with something nonpolar like oil, does that work? They don't mix. Because if you would mix oil in here, so you got oil molecules, you stir it up, you shake it and agitate it, and you get the molecules distributed among each other. It might look like it's mixing, but you said it, and then after a minute or so, they'll separate. Because the water molecules with these hydrogen bonds are pulling each other together. The nonpolar molecules are not attracted to the water or to each other, so they just get squeezed out of the way. So you end up with all the water molecules together, and they usually sink to the bottom. The oil will go to the top, just because water is heavier or denser than oil. So they'll be in separate layers, just because of that polar and nonpolar. And so polar stuff like sugar is polar molecules. So sugar dissolves in water just fine. Polar dissolves in polar. Polar and nonpolar don't dissolve. But what about nonpolar and nonpolar? Can you mix something like gasoline and oil together? Does that work? They both dissolve just fine. In fact, there are some gasoline engines that you're supposed to add some oil to the gasoline. They're called two-stroke engines, like outboard motors for boats. So, okay, well, time's up. We'll try and finish this chapter Monday. Have a good weekend. Oh, don't forget, if you haven't done the introductory quiz on Moodle, it needs to be done by midnight tonight.
gracias por eso. Yo sabía.